Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hey there, Herman and Corin. So I'm listening to episode number 2 about VHB tape. And I think these episodes are gems because if anyone asked me how my AI-generated podcast is going, I would say, and what's good about it, I would say, well, there's kind of just these random things I find interesting and want to know about. And I don't think anyone's made a podcast about them before. So not only have we, I think, possibly made the first podcast. Definitely, I'd be amazed if someone's made a podcast series about VHB tape because we're now going into episode 3, and this is the beauty of the podcast. You find these random details, and I ask more questions. So VHB, for anyone who hasn't joined the 2 previous episodes, is very high bond strength tape, and I shared how, as a renter, and as a tech enthusiast, one of my long-standing frustrations is trying to mount things when you can't drill or, adhere stuff properly. And I can't even tell you how many times I've tried to stick different things onto different surfaces and they just fall off. And I asked ChatGPT one day, well, what's the strongest tape that you can buy? And thereupon I discovered VHB. So we've mentioned that VHB has been used in the Burj Khalifa to attach glass onto the metal frame, which is truly amazing. We mentioned that at the kind of high level altitude we're talking about here and the level of wind exposure at that altitude, concentrating, and especially the heat, those conditions in Dubai, that if we had just screws in place, that the uneven thermal expansion between glass and metal would be a hazard, and VHB, not just a hazard, it would break. And the fact that VHB, or just an adhesive, spreads it out is a recipe for success. Now, you mentioned in that episode that VHB is also used in airplanes, and we didn't really dive into that, which is what I'd love to talk about in this episode. But as a shared prompt, so I mentioned I'm using VHB all over the place now. It's brilliant. And, there is these rules of kind of application, surface preparation with isopropyl alcohol. We mentioned heat really helps a lot for chemical reasons. Pressure, pushing down really hard for a minute or so, and then 72 hours ideally for the maximum, for the bond to reach its strength before putting on a weight-bearing load. And my question is, I have 2 questions for this, our 3rd episode about VHB. Number 1, its use in aircrafts. Please expand upon that. I'm really curious because it's one thing to know that the Burj Khalifa, which I may never visit, and some skyscrapers are using this stuff. But when you say it's used in airplanes, and it's certainly used in automotives, are you talking about like the things we might be flying on? What kind of use does it see in the world of aviation? And secondly, aviation is, of course, kind of the gold standard for safety. So the reason I mentioned my application process, or what I'm doing, is because I imagine that in these most demanding applications, the application has to be done, as professionally as possible. You can't have someone just, I'm kind of picturing someone taking the back off a piece of VHB tape, pressing on a wing and saying, hey, I think that's a solid fit. I'm just kidding. I doubt it works like that. And of course, wings are welded onto airplanes. But in its applications, in those really mission critical applications, I'm just curious to know, how is the application done to meet those exacting standards and these impressive applications? Over to you, Herman and Corin.
Hey everyone, welcome back to My Weird Prompts. I am Korn, and I am sitting here in our living room in Jerusalem with my brother, the man who probably knows more about industrial adhesives than anyone else in this city.
Herman Poppleberry at your service. And Korn, I will take that as a compliment. Adhesives are the unsung heroes of the modern world. If you look around this room, half of what we own is likely held together by some form of chemical bonding rather than a screw or a nail.
It is true. And speaking of things being held together, our housemate Daniel sent us a follow-up to our previous discussions on very high bond tape, or VHB. He was listening to our earlier episodes and wanted to go even deeper. Specifically, he is curious about how this stuff is used in aviation and the automotive industry.
Daniel always has a knack for finding the most interesting technical rabbit holes. I love that he is pushing us on this because aviation and automotive are where the stakes are the highest. We are talking about environments where failure is not an option. You cannot just have a piece of an airplane falling off at 30,000 feet because the tape lost its stickiness.
Exactly. And I think that is the hurdle for a lot of people to clear mentally. When we think of tape, we think of scotch tape or duct tape, things that are temporary or for light duty. But when we talk about VHB in a mission-critical context, we are talking about a permanent structural bond. So, Herman, let us start with the big one. Aviation. Where are they actually using this stuff on an airplane?
It is more common than you might think, but we have to distinguish between structural and non-structural applications. In the world of aviation, anything that carries the primary load of the aircraft, like the main wing spars or the fuselage frames, is still largely riveted or bolted, though even that is changing with carbon fiber composites on planes like the Airbus A350. But VHB tape has found a massive home in what we call secondary structures and interior components.
Okay, so when I'm sitting in my seat, looking at the overhead bin or the side panels, is that where the tape is hiding?
Precisely. One of the biggest applications is for interior panels, ceiling panels, and floorboards. If you use screws for every single panel inside a Boeing 787, you would be adding hundreds of pounds of weight just in fasteners. Not to mention, every screw hole is a potential point for a crack to start due to metal fatigue. VHB allows manufacturers to bond those panels to the airframe smoothly. It creates a continuous bond along the entire length of the panel, which distributes the stress evenly rather than concentrating it at a few screw points.
That makes a lot of sense from a weight perspective. Every ounce matters for fuel efficiency. But what about the outside of the plane? Is there tape on the exterior skin?
There is. One of the coolest applications is for what they call skin-to-frame bonding on non-pressurized areas. Think about the fairings, which are those smooth covers that go over the gaps between different parts of the plane to reduce drag. Many of those are held on with high-performance adhesives like VHB. Also, the de-icing boots on the leading edges of the wings of many turboprop planes are often bonded using specialized adhesive films.
Wait, the de-icing boots. Those are the rubber membranes that inflate to crack the ice off, right? That seems like a very violent environment. The air is screaming past at 300 miles per hour, and the rubber is literally expanding and contracting.
It is a brutal environment. You have extreme cold, high-speed wind, and the physical stress of the inflation. But that is actually why an adhesive like VHB is better than a mechanical fastener. VHB is viscoelastic. That is a fancy way of saying it acts like both a liquid and a solid. It can absorb the energy of those vibrations and the expansion of the boot without fatiguing. If you used rivets, the constant vibration and movement would eventually cause the rivet holes to elongate or the metal to fail. The tape just moves with it and then snaps back.
So it is almost like a shock absorber and a glue at the same time.
Exactly. That is the genius of the acrylic foam core. It allows for what we call stress relaxation. If the wing expands because of heat or the plane flexes during turbulence, the VHB layer stretches slightly to accommodate that movement. It prevents the two bonded surfaces from ripping each other apart.
That is fascinating. Now, Daniel also asked about the automotive industry. I imagine it is a similar story there, but maybe on an even larger scale because of how many cars are produced.
Oh, the automotive world is obsessed with VHB right now, especially with the shift to electric vehicles. In a traditional internal combustion engine car, you use it for trim, emblems, and those plastic spoilers on the trunk. But in electric vehicles, weight is the enemy of range. Every kilogram you save is more miles you can go on a single charge. So they are using VHB to bond battery components, thermal management systems, and even structural reinforcements inside the doors.
I read somewhere that Tesla and other manufacturers are moving toward more adhesive bonding to simplify the assembly line. Is that part of it?
It is a huge part of it. Think about the robots on a car assembly line. If you are welding, you need massive amounts of electricity, you create heat which can warp the metal, and you have to deal with toxic fumes. If you are using tape, you just have a robot arm, apply a precise strip, press the parts together, and you are done. There is no heat, no distortion, and the bond is instantaneous. Plus, you can bond different materials together, like aluminum to carbon fiber or plastic to steel. You cannot weld those together.
That is a great point. Galvanic corrosion is a real issue when you put different metals together with a metal rivet. The tape acts as an insulator, right?
Spot on, Corn. It creates a physical barrier so the two metals never actually touch. That prevents the electrochemical reaction that causes corrosion. It is a huge deal for the longevity of the vehicle, especially in places where they salt the roads in winter.
Okay, so we have established that this stuff is incredibly strong and versatile. But Daniel's second question is really the heart of the matter. How do they manage the application process? If I am a technician at Airbus or Ford, I cannot just slap some tape on and hope for the best. There has to be a rigorous protocol.
This is where it gets really intense. In mission-critical industries, the application of an adhesive is treated with the same level of scrutiny as a structural weld. It is not just peel and stick. It is a multi-stage process that is strictly documented and controlled.
Walk me through it. If we are bonding a fairing onto a wing, what is the first step?
Step 1 is always surface preparation. This is where most DIY projects fail. In a factory setting, they use a specific cleaning agent, usually a 50-50 mix of isopropyl alcohol and water, to remove every single trace of oil, dust, or fingerprint. Even the oils from your skin can ruin a high-performance bond. In some cases, they will even use a mechanical abrasion, like a light sanding, to increase the surface area and give the adhesive more teeth to grab onto. They might even use something called a dyeing pen to measure the surface energy and ensure the material is ready to accept the bond.
And I assume they are doing this in a clean room environment?
For the most critical parts, yes. Temperature and humidity are strictly controlled. If it is too cold, the adhesive becomes too stiff to wet out the surface. If it is too humid, you might trap moisture under the tape. They have sensors everywhere to ensure the conditions are within the specified range before the tape even touches the metal.
You mentioned wetting out. I have heard that term before in your nerdy rants. What does it actually mean in this context?
Think about a drop of water on a freshly waxed car. It beads up, right? That is poor wetting. Now think about a drop of water on a piece of paper. It spreads out and soaks in. That is good wetting. For an adhesive to work, it has to flow into all the microscopic valleys and peaks of the surface. VHB is designed to do this over time, but the initial application needs pressure to force that contact.
So the pressure is the next big step.
Yes. In aviation, they often use specialized rollers that apply a specific amount of force. It might be 15 pounds per square inch of pressure. Some parts are even put into vacuum bags or autoclaves to ensure that the pressure is perfectly even across the entire surface. This forces the adhesive into the pores of the material. Without that pressure, you only have about 20 or 30% contact. With the right pressure, you get closer to 100%.
And then there is the waiting game. I remember you telling Daniel that it takes 72 hours for VHB to reach full strength.
That is the standard for the typical acrylic chemistry. About 50% of the strength happens in the first 20 minutes. After 24 hours, you are at 90%. But for a mission-critical part, they will often wait the full 72 hours before that part is allowed to see any significant load. They are tracking this with timestamps. Every part has a logbook. It says exactly when the tape was applied, who applied it, what the temperature was, and when it is cleared for the next stage of assembly.
That level of traceability is wild. It is like every piece of tape has its own birth certificate.
It really does. And they also do what they call coupon testing. While they are bonding the actual part, they will bond two small scraps of the same material using the same tape and the same process. Then they take those scraps, or coupons, and pull them apart in a machine to see exactly how much force it takes to break the bond. If the coupon fails, they know something went wrong with the process, and they can reject the main part before it ever leaves the factory.
That is such a smart way to verify the quality without destroying the actual airplane part. Now, what about the long term? An airplane is expected to fly for 20 or 30 years. How do they know the tape won't just dry out or get brittle?
That is the beauty of the acrylic chemistry in VHB. Unlike rubber-based adhesives, which have double bonds in their molecular structure that can be broken down by UV light or oxygen, acrylics are saturated. They are incredibly stable. There are VHB bonds out in the world that have been exposed to the sun and rain for over 40 years and still have their original strength. In the aviation industry, they perform accelerated aging tests where they blast the bond with UV, cycle the temperature from -60 to over 100 degrees Celsius, and soak it in jet fuel. VHB passes those tests with flying colors.
It is amazing that a chemical bond can be that durable. It makes me wonder about the future. If we can trust tape to hold a plane together, what else can we do with it? Are we going to see cars that are entirely glued together?
We are already getting close. If you look at high-end supercars from companies like Lotus or McLaren, they have been using structural adhesives for their chassis for years. The automotive industry is moving toward a multi-material approach. You might have a car with a carbon fiber passenger cell, aluminum subframes, and plastic body panels. You cannot weld those together. Adhesives are the only way to join those disparate materials effectively.
It feels like we are moving away from the mechanical age, where everything was bolted, and towards a chemical age of construction.
That is exactly right. And it is not just about strength, it is about acoustics too. One thing people do not realize is that adhesives make cars and planes much quieter. A rivet or a bolt is a bridge for sound and vibration. A layer of VHB is a barrier. It damps the sound. If you ever ride in a modern luxury car and marvel at how quiet it is, you can thank the miles of adhesive bonding that are absorbing the road noise.
I never thought about that. It is a silent contributor to the experience. Now, Herman, let us talk about the what-if scenarios. What happens if a bond does fail? Is there a redundancy built into these systems?
Always. In aviation, they follow the principle of fail-safe design. If a bonded panel were to fail, there are usually secondary mechanical stops or overlapping structures that prevent the part from completely detaching. Also, the inspection cycles are very rigorous. Technicians use ultrasonic testing or infrared thermography to look inside the bond. They can actually see if there is a void or a delamination starting before it becomes a problem.
Ultrasonic testing? Like an ultrasound for a baby?
Almost exactly like that. They bounce sound waves through the material. If the bond is solid, the waves pass through or reflect in a predictable way. If there is a gap or a failure, the sound wave hits that air pocket and bounces back differently. It allows them to see the health of the tape without ever touching it.
That is incredible. I love the idea that we've developed technology just to check on the health of our tape. It shows how much we rely on it.
It really does. And you know, Daniel mentioned in his prompt that he uses it as a renter to mount things without drilling. It is the same basic chemistry, just at a different scale. The fundamental physics of surface energy and viscoelasticity are the same whether you are hanging a picture frame in a Jerusalem apartment or bonding a panel on a fighter jet.
It is a nice bit of symmetry. Though I hope Daniel is cleaning his walls with isopropyl alcohol before he sticks anything up.
I have seen his work, Corn. He is pretty meticulous. But I should probably give him a hard time about his wet-out time next time I see him in the kitchen.
Oh, please do. He will love that. So, to wrap up the technical side, what is the biggest challenge facing these industries right now when it comes to adhesives?
I think the biggest challenge is the human factor in the application. Robots are great, but a lot of this work is still done by hand. Training technicians to understand the importance of surface prep is huge. You have to treat it with the same respect as any other high-stakes engineering process. Also, recycling is a big topic. If you glue a car together perfectly, how do you take it apart at the end of its life to recycle the materials? 3M and other companies are working on debondable adhesives that lose their strength when hit with a specific trigger, like a certain temperature or a specific frequency of light. This is critical for the circular economy, especially for recycling EV batteries.
That is the next frontier. Permanent when you need it, but removable when you are done. It sounds like science fiction.
It is happening right now in the labs. It is a very exciting time to be an adhesive nerd.
Well, Herman, I think we've given Daniel and our listeners a lot to chew on. It is fascinating how a simple concept like tape can be pushed to such extreme limits.
It really is. And it just goes to show that there is no such thing as a simple topic if you look closely enough. Everything is a miracle of engineering if you go deep enough.
I couldn't agree more. This has been a great deep dive. And hey, for everyone listening, if you have found this interesting and you want to help us out, a quick review on your podcast app or a rating on Spotify goes a long way. It helps other curious people find the show.
It really does help. We appreciate every single one of you who takes the time to do that, and thanks again to Daniel for sending in this prompt. It gave me an excuse to talk about viscoelasticity for 20 minutes, which is my favorite thing to do.
We know, Herman. We know. You can find more episodes and get in touch with us at myweirdprompts.com. We are also on Spotify and wherever you get your podcasts.
This has been My Weird Prompts. Thanks for listening, and we will catch you in the next one.
Goodbye, everyone.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox Turbo.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.